This talk is about imaging quality control when it comes to digitizing two-dimensional objects, especially for cultural heritage applications. So first, let's have a short overview over the topics. First of all, we want to see why we need an image quality control. And then we want to make clear that image quality can be measured. We see the technical approach behind, and we have an overview over the standards and guidelines for image quality. And at the end, we are looking into practical implementation of an image quality control system. So let's have a look into the goals of cultural heritage digitization. First of all, the digitization creates a digital copy of the original. And this copy further on refers as a representative of the original for long-term preservation purposes. It reduces the number of times you need to access the original, and it serves as a master for reproduction purposes, especially when you're doing facsimiles. For further research purposes in remote access and further processing like OCR are typical in these applications. The picture resembles the original as closely as possible in the geometric appearance, in its details and structures, in brightness, contrast, and gradation, and last but not least, in the color rendering. However, well matched is different for different people. That's why image quality must be fully defined and above all measurable. Let's have a look at two images. Both are sampled with 300 ppi resolution. The left one we would like to receive, the right one is definitely nothing what we would like to have. The same with color imaging. Both have a color depth of 24 bit per channel, but only the left one appears to be correct. And most important is image quality is measurable. This can be defined by using different parameters, such as there are resolution, geometry and distortion, channel registration, noise, linearity of the tonal value gradation, that's the OSCF, dynamic range, and color reproduction. Homogeneity of illumination is important, and also we are looking into the situation with the artifacts. The values of the above parameters can all be measured in a scan of a test chart. For each of these parameters, there are at least one measurement method that can be used as a best practice. These methods are described in international ISO standards, and the image quality thus can be defined via limits for the above parameters. So let's have a look into the technical approach. The image quality is determined by digitizing and evaluating the image of the test chart. The single structures inside the chart can be analyzed and evaluated by the measurement software. And this gives us a quantitative result of the image quality achieved. And with that, we got a statement about the image quality performance of the equipment in use. The measurement results can be compared against a set of specifications for image quality. If you digitize books or documents with the same settings on the same system you have measured, the previously measured image quality is also representative for these digital copies of your documents. So let's see how this process works in the flowchart. In the center, of course, we have the imaging system. Then we have our multi-pattern test chart, which is digitized with the imaging system. We got the imaging specifications. This means the aims and tolerances we are currently using. And we have the analysis software for imaging quality. And of course, we have reference values from this multi-pattern test chart, which are going into the analysis software. We do the digital output of the imaging system and lead this into the imaging quality software. And the third party is the imaging quality specifications. After that, after analysis, we got a result report. And if this result report is in line with the specifications, we can go on and we can start our digitization if it's passed. If not, we have to do readjustments on the imaging system. So in the next round, we hopefully get a result which passes the test. What is the reference data we have for the multi-pattern test chart? First of all, the individual values of the structures inside the test chart. They are stored in this reference file for the test charts. These can then be taken into account by the measurement software, And with this, the individual protection tolerances of the test chart are excluded from the measurement process. So the image quality specification is defined by a list of required aims and tolerances for the single image quality parameters during the measurement. The software compares the measurement result against these aims and tolerances, and with this, the measurement result provides an information whether the image quality meets the requirements or not. These aims and tolerances can come from your personal experience, or the values can be taken from technical guidelines, such as Metamorphose or Fudgy guidelines, or better from the ISO standard 19264-1. So the typical technical guidelines in use are the Metamorphose imaging preservation guidelines, which were first laid out in 2010, and the next version probably will be available in 2022. Then we have more for the US market, the technical guidelines for digitization of cultural heritage materials, released in 2010, and the last revision was in January 2016. And then we got the integration of all these guidelines into the ISO 19264-1, while Fudgy is still not completely integrated. The ISO standards for imaging qualities are the row from 19262 to 19264-1, while the 19264-1 is the most important standard for that. Here are all the information contained about the measurement procedures. Let's see how image quality control takes place in practical work. Here we typically have a sectional quality control. This means in digitization projects, the image quality is measured in a punctiform manner, usually at the beginning or the end of an object, like a book, or a group of similar objects. In larger projects, we have typically tested the image quality in sections or intervals, like start or the end of a shift, or when there is a change in the digitization process. With the latest developments, we can achieve 100% inline quality control in a scan project. The approach is that we are using a small test target, like this object level target here, and this target is digitized together with the originals, and the software analyzes the structures inside the targets with every scan. And with this, we have a verification of the image quality of each copy during the scan process to 100%. We can use the information if we passed the quality level and add this to the image file in EXIF data. This inline quality control is available with the scan software OmniScan 12.12 SR2 and the image quality analyzer software OSQM Tool 1.0 with the option SW2059. Thank you for your attention and questions, please.